Let's do that then. Okay. So we are very happy to have our own Rahul Vaze tell us about network speed scaling.
All right. Can you hear me all well?
Yes.
All right. So thanks, Arkadev, for organizing the talk. This is some joint work which is going to appear in performance this year. This is like a winter sigmetrics, and this joint work with Jaykrishnan Nair from IIT Bombay, who is also online. So if you have some questions, you can also ask him in the chat. I'll be happy to answer. And I'll be happy to answer as many questions, because doing this remotely, I'm sure this is much more difficult to understand. So I won't mind you just jumping in with a question. So let me just begin with a very simple setup, which will help us introduce the problem. So here is the simplest possible scheduling problem. So there is a single server which can run at a fixed speed, and jobs are going to arrive over time. What you want to do is to define something what is called as a job flow time. So this is the time between the arrival and the departure of a particular job. So a job flow time is defined to be the difference between when the job arrives and when it departs. And what you want to do is to minimize the flow time summed across all jobs when preemption is allowed. If preemption is not allowed, then the scheduling problem is kind of trivial. It's only when preemption is allowed the scheduling problem becomes interesting. And what we know is that the optimal algorithm is in fact what is known as SRPT, serve the job with the shortest remaining processor time. So every time you look at the job which has the least amount of work remaining, you pick the jobs and process it and keep going on. And that is an optimal algorithm.
How does arrival timing stream matter in this?
Doesn't matter.
Doesn't matter. Okay. Right.
Yes. So good. So now it's slightly more complicated. So earlier we said it's a fixed speed server. Now we are going to make the server speed a tunable parameter. So you can actually choose what rate at which you want to serve these jobs. And now in addition to the flow time as our cost, there's also, if you want to run this processor at speed S, you have to pay a cost of P of S, which is essentially a power cost. And P is typically assumed to be a convex function. Most often it is just assumed to be a very simple form, which is P of S is just S power alpha. But any nice convex function is fine. All of this will go through. And now in addition to the flow time, we add a penalty, which is with respect to the total energy we are going to spend. And the job is to now minimize the sum of flow time plus the total energy. So if you increase the speed, you decrease the flow time, but then you increase the energy. So there is a trade-off between the two, and you want to minimize the sum of the two. There are many other ways in which you can formulate the problem, but here is the simplest and the most elegant way. And now the optimal scheduling algorithm remains SRPT. The interesting decision choice now becomes what is the optimal speed choice? And that is a non-trivial question to answer. So one way you can set up this problem is just writing it as flow time, which is the summation of flow times across all jobs. An alternate way, which actually helps, is to do the following. So look at any point of time t, look at the number of outstanding jobs in the system, and let's call them n of t. The flow time is also an integral of n of t across time. And the easiest way to see is the following. So let's suppose there are 4 jobs in the system which are going to arrive. And this rectangle essentially represents the total time they're going to spend in the system. So now look at any fixed time t and look at the number of jobs which are available at that particular time. So flow time is equivalently essentially the integral of n of t. In my earlier definition, flow time is just the area of these rectangles where the height of the rectangle is just 1. So alternatively, you can either write it as a summation or an integral, and this integral formulation actually helps a lot. So every time I say flow time, I'm actually going to mean that it's an integral of the number of jobs in the system. So n of t is also sometimes called as the holding cost of the system. So how many jobs are you holding at any particular time? You would like that to be as small as possible, and you're going to trade it off with respect to the speed at which you're going to operate. And the total cost is nothing but the integral of n of t dt plus the energy, which is integral of the power, which is p of s of t. So s of t is the speed at time t, p is the power function we are going to wrap it around, and then the integral is just an energy. So this is the reason essentially writing the flow time as an integral helps. That both these costs are essentially one integral, and some techniques can be applied because this is an integral form. So what we are going to be interested in is what we can say about this problem, which is called a speed scaling, where speed is tunable in networks. So typically it's looked at with few nodes in the network, but now we're going to make it a general network setting where there are multiple source destination pairs. So S1, S2, S3, and S want to send their respective information, or the packets arriving at S1 is meant for destination D1 and so on. And a natural extension of the earlier cost is just add it across all sources and add the power across all the nodes in the network. So the flow time is getting counted across all the sources, and the energy cost is getting counted across all the nodes in the network which are going to operate. So some of the nodes may not be useful, but we're just going to pretend that the speed at that point is 0. So this is a network-wide cost function, and you want to minimize this, where the decisions to be made are threefold. Each node needs to decide at what speed is going to work. The source is going to define how the packets are going to get routed, and also the scheduling part, that if there are multiple packets at a particular node, which packet should a particular node process first. So threefold decisions, and this is the cost function. So if this might be a good time to ask a question on the problem formulation before you move ahead.
Yeah, what is known on this, Rahul, before you guys?
We get there. Yeah.
Okay.
Just a minute.
Okay.
So Rahul, who decides where the jobs are to be routed? Which server would
So the decentralized nature of the problem is not important. Anybody can decide. You can decide from looking at the whole network. So we're not worried about decentralized setting of the network. A centralized controller can look at the whole state of the network and decide. That is okay.
I see.
So, Rahul, so
Yes.
there is a single source and packets will arrive only there.
So there are, if I understood the question, you're saying there is a single source or multiple sources, or?
Yeah.
So there are multiple sources.
Okay. So, and packets arrive and their arrival times are not within our control.
Right.
And then they need to be, each packet comes with its own destination where it wants to get to.
Yes.
And
Yeah.
and while route, I mean, we need to make the decision online as packets arrive, or we have global information of all the packets that are going to arrive in the next day.
No. So we are going to look at only online algorithms where at time t, you only know causal information. You know information about what's going to happen in the future. We'll also look at the stochastic case where you don't know the exact realization of what's going to happen, but at least some distribution is known.
Yeah. And the decision at a node has to be made based on information it has already received, or it can also see things a little bit into the future based on what other nodes are doing right now.
No. So at any point of time t, the decision is causal. So nothing about future is known. But if you can predict something about how the packet is going to be, so if at a certain time, a particular node is holding a packet and it notes where that packet is going to go to a destination, that information can be used.
So his point is, does the node, while making, first of all, is a node making a decision or is it centralized? And secondly, is all the information on the network known, the causal information at that time?
Yes. Yeah, so we are not making any assumptions about lack of information or limited information is completely known, but it is causal. That's all.
And centralized decision making.
And centralized decision.
I guess it doesn't matter, but the packets can be of different sizes also, right?
For the worst case setting, you're going to assume that all packet sizes are also equal. The worst case essentially means all the timing information is worst case.
Okay.
Which packet arrives at which node and at what time. But all packet sizes are going to be equal. Good. All right, so now I'll answer Sandeep's question. Before that, let me set up the problem in the online algorithms context. So what do we mean by an online algorithm? Let me redefine that. At any point of time t, an online algorithm has only causal information, but it's going to compete against an offline algorithm which knows everything in the future. And we are going to look at the cost of these two and take the ratio of them. So an online algorithm is represented by ON, and an optimal offline throughout the talk will be OPT. And what we are going to look at the cost of this online algorithm and take the ratio with respect to the optimal offline algorithm, which knows the input sequence in advance, and then look at the worst possible sequence which can be given to a particular algorithm. So that's what is going to be defined as competitive ratio for a particular online algorithm. our quest is to find an algorithm which has the minimum such competitive ratio.
So Rahul, wouldn't it make sense to compare with the best algorithm which knows all the information till time t at time t?
So it's a more reasonable thing, but it becomes difficult. And essentially what ends up happening is that most often you're able to say that this ratio itself is a constant. If it's not, then one wants to look at saying, okay, can I look at the best possible online algorithm? But that becomes generally harder. So that's why this metric is used. It's a very pessimistic metric, but as long as you can say something interesting, things are okay.
Wait, I'm a little confused with Sandeep's question. So if you only compare it with algorithms that know only what has happened until now, then this ratio is just 1, right?
No, among all online algorithms. So for a particular algorithm, you may not be the best online algorithm, right? Because we don't know what the best is.
Oh yeah, no. But I'm saying if you're going to
Minimize over all, yes, then it's
okay. Yes, okay. If you want to find the best algorithm in that ratio, it will just make it 1.
Correct, but this is for a particular algorithm.
Okay.
And in the stochastic setting, we're going to take a slightly simpler view where everything is going to be an expectation and there is no max over the input. The input itself is stochastic. So for a particular stochastic input, we're going to look at the ratio of the two and then call that as a competitive ratio. And our goal is to find an algorithm with least competitive ratio, which often is not achieved. So we'll see how much small can we really make the competitive ratio. All right, so what do we know? So this single server setting is actually very well understood in the speed scaling literature. There's a large body of work which eventually got resolved by a famous paper by Nikhil Bansal and his co-authors, and which was further improved by Andrew Laplan and Adam Bierman in 2010. So what they showed is the following, that if you recollect, the scheduling algorithm is SRPT, which is optimal. So always schedule the packet which has the least service remaining. And at time t, if n of t is your number of packets which are outstanding in the system, use the speed to be p inverse of n of t. So p, remember, is the power function I'm using, that if you run at speed s, the amount of power you need to spend is p of s. So essentially what they said is that if you choose the speed to be p inverse of n of t, you can achieve the best competitive ratio, which turns out to be 2. So both a lower bound and an upper bound. So Bansal's paper gives only an upper bound. This follow-up paper actually also constructs a lower bound and says that you cannot do anything better. So
is it, I mean, does this roughly correspond to you invest proportional to the number of waiting jobs?
Right. So I was about to say that if you take p on the left-hand side, the power you're spending is exactly equal to n of t. So n of t is the number of packets in the system at time t, and the power you're investing is also n of t. And that turns out to be the best you can do in an online setup.
The assumption on P is that it's strictly monotone, or is there some other assumption?
Sorry, say it again.
The assumption on P is that it's strictly monotone, or is there some other assumption also?
Convex, differentiable, all sorts of things are there.
Other assumption
You can remove the differentiability part and still the result holds.
Other assumption also.
Say it again, please.
No, that's fine. That's fine. Thanks.
Now the second interesting setting, which also got a lot of attention, was a setting of parallel servers. So there is a single stream of data arrivals, and there is a bunch of servers available. Any arriving job can be sent to any of the servers. It can't be split, but it can be sent to any of the servers. And servers can potentially have different power functions. So again, there's a lot of work, and the best known work is by Nikhil Devanur in 2017. So, and the algorithms of the following type. So in this case now, compared to the single server setting, we don't know what the optimal scheduling strategy is. So SRPT is no longer optimal. So nobody makes a claim about what the optimal scheduling is, but finds for particular scheduling algorithms and particular speed choices what you can get. So Anupam Gupta in 2010 showed that alpha is the parameter of the power function. So P of S is equal to S power alpha. So this is the function which most people employ. So it might appear in a lot of slides. So it's good to remember this, that we're going to mostly concentrate on P of S is equal to S power alpha. And the guarantees you can get are always in terms of alpha. So there is no rigorous proof as such that you cannot avoid the dependence on alpha, but most people believe that alpha is there. So there's no lower bound as such that says that you cannot avoid alpha, but all the guarantees we know in the past are always dependent on alpha. And the best bound is by Nikhil Devano, which says that an algorithm exists, or they actually construct an algorithm which has a computative ratio of 2 times alpha. Recently, what we did was we looked at a very simple algorithm, which is a multi-server counterpart of SRP. So you have, let's say, k parallel servers. Pick the k shortest jobs to serve always. And then for that, you can show that it is slightly larger than the Devano guarantee, but at least there is a guarantee with respect to the multi-server SRPT algorithm, which is very easy to actually implement. So this, as far as we knew, was missing, and we recently did this and appeared in, this year in transaction network.
So what is f sub I in the earlier?
So they construct some functions for each server, and so I'm not going to go into details of that, but each server maintains a particular function and decides to assign a newly arriving job dependent on that, on the current load and the new job. So that's the algorithm of the type. So I just wanted to distinguish with respect to multi-server SRPT. SRPT is very simple. It doesn't maintain anything. It just looks at among the all outstanding jobs, pick the ones which are the shortest and assign them to the k servers you got. All right. So now question is, what do we know for networks? And as far as
Rahul, what happened to stochastic settings?
we'll come to that. So I'll separate the stochastic setting versus the worst case setting. So stochastic setting for a single server and multi-server, similar results are available. So what do we know for networks is the major question. And as far as we know and as far as the reviewers know, not much. So I'll definitely point out that there is large body for networks when they look, the question is slightly different, and the question is of throughput optimality. So what one wants to find out is, suppose each edge on the network is capacitated. So there is a capacity associated with each edge. What you want to find out is an algorithm which can stabilize all the queues. I'll define what stabilize in a minute. So all queues for the largest set of arrival rates into the sources. And by stability, we mean that the queue lengths don't blow up to infinity. So let me be not very rigorous here, but and there's like just too much work on this for like last 30 years. So I'm not going to review all of them, but if you want to know, I'll point you out to the relevant references. So the bottom line is this: essentially, for the question we are asking, where delay is directly being counted as a cost function, delay and energy, we don't know much about how to do things with the networks, and that is what the topic of this paper is.
Rahul, I have a question.
Yes. Yeah.
So do you also allow like multicast type of traffic, or is it always unicast? Is there a packet duplication inside the network?
No. So this is
Okay.
much very simple. Everything is wired. One packet doesn't ever get copied anywhere. Things are very simple.
Okay, and you're also going to propose another control mechanism for routing, right? I mean, routing is also a skid decision.
Right.
Okay.
Yes.
Okay. Thank you.
So let's begin with a very simple network. So I said bold claims about networks. So before making any bold claims about general network, let's start with a line network. So there's a single source, single destination, and there are a bunch of servers in between. So every job which arrives at S1 has to be processed by each of these K servers before it can go to D1. And all these servers have the same power function. So the algorithm we are going to propose is the following, that every time a server has a job to process, all of them are going to run at the same speed, which is given by P inverse of this, where I'll define what these terms are. So N of T is the number of jobs waiting in the first server. And A of T is just the number of servers other than the source which actually have a packet waiting at them. And other than the first server, because of the condition that all servers are going to run at the same speed, there is at most one packet at each of these intermediate nodes. So they cannot have more than one packet. So that is why AT just counts the number of these servers or nodes which have a packet to process. And what we are doing again is very similar to the Bunzel type speed scaling. So N of T plus A of T essentially is the total number of packets in the system. We are scaling it down by the denominator also is scaling it down by A of T, because now there are A of T servers which are working in simultaneously, and we want to control the total power spent in the system. So this is essentially normalizing the total power in the system. If there was single server, A of t will be essentially be 0. So this is slightly more complicated than the single server problem. So what is happening is that speed is continuously changing or discontinuously changing as soon as AT changes. So AT keeps changing as soon as jobs move from one server to the other, potentially filling up AT equal to K. So maximum value of AT can be K. So as it increases, the speed is actually discontinuously decreasing. But that decrease is to make sure that the total power used in the system is again n of t plus a of t, which is nothing but the total number of jobs in the system. So that's the motivation for considering this particular speed choice. That is power spent in the total power spent in the system remains n of t plus a of t, which is the total number of packets in the system. So what you can show doing this is that the competitive ratio for any alpha is bounded by alpha times something which is independent of alpha in the sense that it's just a power function dependent recursive equation and can be solved straightforwardly for any alpha. For alpha equal to 2, which is of primary interest, the competitive ratio turns out to be 18. More importantly, this is independent of the network, which is it doesn't depend on the number of packets in the system or the total number of packets going to arrive in the system or the number of nodes in the system. So that is what the main takeaway is. The number 18 is not that important. It could have been 36 and you would still be happy. So the quest really was to first get over the dependence of a network. A naive policy will essentially get you a dependence over K. This particular choice and the ensuing analysis will make sure that the competitive ratio remains constant. It's independent of the network. So let me now recap why do we need all this complicated speed business and not somehow use what we know for a single server setup. So the natural question that can pop is, why can't I just use what I know for single server and keep doing this in sequence? So the difficulty is as follows. So what happens is that the external packet arrivals are happening into server 1. So let's say the first packet arrives. Our speed scaling for the single server system will make sure that you run at speed P inverse of 1. After that, it goes to the second server. Again, because of the single server being present in the second system, it's again going to run at P inverse of 1. But now assume that a lot of packets arrive suddenly in server number 1, at which time the speed will be ramped up for server number 1. Now this green packet will depart server 1 and reach server 2 before the red packet is finished in server 2. So compared to a single server system, what is going to happen is that the green packet is going to see different delays on server 1 and server 2. If somehow I could combine or relate the two, there was possibly a way to get away by using just a single server solution for a multi-server solution, but that actually does not work. And using these kind of simple hacks of like using the single server solution to a series server solution doesn't actually work out. And that's the major reason that the delays seen in different queues could be completely different and you will not be able to correlate them. So now I'll very, very briefly go over like what are the basic tools available. These are not what we have come up with. These are classical tools, but they help us even extending the single server problem to the multi-server problem. So the basic idea is what is called as potential function. In networking community is also known as Lyapunov function. Let me just go over this in a very...
Rahul, before you go further, are you going to suggest another algorithm as well for this series setting? Or is
no,
it...
the algorithm we presented was already there, and the guarantee also I suggested the competitive ratio is going to be 18 for that particular algorithm.
There's no easy improvement to that you can see.
This is the best we know right now. And this is fresh from the oven. So let's look at this, how to use the potential function idea. So recall that the objective function for an algorithm is flow time plus energy, which is integral of the number of packets in the system and this current speed of the system wrapped around with the function P. Similarly, you can say for the OPT, so OPT knows everything in the future, so it could use whatever it uses and keeps possibly a different number of jobs in the system N0 of T and uses a different speed S0 of T, which we don't know. We actually don't know what the optimal algorithm is going to be. So this is going to be something unknown. But now assume that there exists a potential function phi of T, some function which is defined for each time T, which has the following properties. That the instantaneous cost, so NA of t plus P of SA of t is the instantaneous cost of the system for an algorithm A. N0t plus P of S0t is the instantaneous cost for an optimal algorithm, which is OPT. Assume that we can show the following property, that the instantaneous cost of the algorithm plus the derivative of this potential function, it's a magical function for the moment, is somehow related to the cost of the OPT, and it's at most C times the cost of the OPT, where C is a constant. So this is all hypothetical for the moment. It's just a definition. Suppose there exists such a function. And in addition, it satisfies two properties, that before the system begins and after all the arrivals have happened and all the departures are done, the function evaluates to 0. And at any, it could possibly have discontinuities, essentially at the places where jobs, at times where job arrives or job departs, but it should not be a positive jump. If it has a negative jump, that's okay. Or if it has no jump, it's even better. So suppose those two conditions are also satisfied, then just integrating the instantaneous cost essentially gives us what we want. So now left-hand side is essentially the cost of the algorithm. Right-hand side is the cost of the OPT, and this constant plays out as it is. So what we end up showing, if suppose such a function exists, is that the competitive ratio of an algorithm A is at most C if these two conditions can be satisfied. So now the quest typically is to find such a potential function phi of t and show that these properties hold. If, for example, you can't enforce that the jump, there are positive jumps and you can't enforce, there is a remedy out that supposing the total amount of jump the function phi of t has is somehow related to the cost of the OPT. So it is some d times the cost of the OPT, then you can again bring the competitive ratio inside and they say that it is at most C plus D. So all is not lost even if it has a positive jump discontinuity. And for all our systems, we'll actually have to incur such a jump discontinuity. We just have to show that it is a constant. So is the potential function idea clear? We want to construct somehow a potential function such that these two properties hold. That the drift or the derivative of phi of t is somehow related to the cost of the algorithm and the cost of the OPT, and they satisfy the boundary conditions. So now why it is difficult to construct? So all the past work I talked about, the single server or the parallel server systems, essentially went through this mechanism of constructing a particular potential function. Why is it harder in a network setting is for the following reason. That what happens is the external arrivals happen into the source, which are synchronized for an algorithm or the OPT, because that's external to the system. Your choice doesn't change anything. And all the jumps essentially in phi of t are because of the arrivals. Departures can be controlled more or less. What is non-trivial is because of this choice of your speed of the system, the transitions happening from one internal server to the other internal server. For example, here from 1 to 2, they are not synchronized for the algorithm and OPT. OPT could use some other speed and it can transition at a different time. And that gives rise to this problem of finding a potential function for which you can control or like there's no way of synchronizing. So it's very difficult to control what jumps there are. And this is essentially what makes this problem harder when there is a line network. So the simplest network where already it is hard to find a potential function compared to a single server system where all the arrivals are external and you don't have to worry about it.
There's no multi-dimensional formulation you can look at. So each cube becomes a dimension and you write the equation separately for them.
So because we're looking at the worst case, such a thing may not be feasible. If it was stochastic, possibly one can do that. So we'll see in stochastic case, things are much easier. So I'm just going to give you one candidate potential function. I don't think I will have time to talk about how exactly it works. So what we're going to do is for the different servers, we're going to define a different potential function. For the first server, we're going to define a potential function where this quantity n of q of t is going to be a kind of a histogram where we look at q as the size of the job and count for each q how many jobs are there with size at least q. So in the picture on the right hand side, for q1, all 4 jobs count. For q2, 2 jobs count. For q3, only 1 job count. So we're just looking at the tail histogram of the number of jobs in the system. So for each q you do this, and the integral is, sorry, so there's a typo here. The integral should be over dq, not dt. So at each time t, we look at for each q, the number of jobs in the system with size at least q. So this quantity is for the algorithm, this quantity for the OPT. And you take a plus, that is max of 0, the quantity here. And there are a few other things happening. This is the total number of internal servers is k, and the function f is defined to be an incremental function with respect to the power function p. So given limited time, I'm not going to spend how we derive this, but all of this is actually very natural given what speed function we are using. For the internal server, it's going to be slightly different. So what the internal server is going to look like is, for let's say the internal server j, we're going to count all the jobs which lie to the left of this j. So that is going to be the first summation here. And for that server j, we're going to count again the number of jobs available at this server with size at least q. So that is going to define dj of qt. And then you define a particular potential function for this server j, which is very similar to before, except now there's a dividing factor with a of t plus 1, where a of t, remember, is again the total number of servers in the system which have a packet outstanding with them other than the source server. So if you have noticed, the potential function for the internal server actually has no contribution for the OPT. And this is precisely the point I was suggesting earlier, that I have no way of controlling or synchronizing the arrivals into internal servers. So that is why I don't even take into account anything which is any contribution from the OPT inside the phi j of t. And because of that, every time dj of q of t increases, that is, every time a new job comes into j, into server j, phi j of t is bound to have an increase. So there will be a positive jump. But because the total number of jobs in the system other than the source is at most the total number of servers in the system other than the source server, dj of qt is always at most a of t. So this ratio is at most 1. So there is hope of controlling, and that is what we do to control the total amount of jumps these internal potential functions can have. So overall, the potential function is going to be very complicated, but this is what it looks like. So for the first server, we define phi of 1. For internal servers, we define phi of j. We take a linear combination of them, and that is what our eventual potential function is going to look like. So each sub part of this is going to give you a drift, which will eventually come back and give the ultimate result. So drift of the potential function is coming from the following reason. So as the algorithm works, it's working at speed s of t, which we know or we can define. So what essentially ends up happening is that the quantity n of qa comma t ends up decreasing by 1. So remember, n of q is nothing but the number of jobs above a certain level q. So at q, you're working an infinitesimal amount, so it drops it by 1. So that's what the change in phi of t looks like with respect to the working of algorithm. For the OPT, we only have that for the phi 1. We don't have it for phi of j because we have not taken any contribution there. And those are the two. So algorithm changes the potential function in so many terms, which are essentially given by a of t of them, while the OPT changes only one of them. And you put it together, and what you show is the following, that the total drift is at most given by the total number of jobs in the system plus the total number of jobs the OPT is carrying. So this is what the magic part is, that somehow it is able to capture what the OPT is doing plus k times the power the OPT is spending. So that's what the drift term looks like after you do all the computations. And the speed choice remains as before. And you can show that the instantaneous cost is satisfied for a particular value of c. As I said, we can control the total jump discontinuity, and you put it together and you get a constant out of all this. So I know this is, it's difficult to pass through in one slide, but that's a very high level view of all things. What you want to do is to control the drift of this potential function and somehow choose the speed in such a way that you get what you want. So speed is the control you have, and that is driving how the drift of the potential function looks like. So one point I should emphasize here, that lower bound in the OPT is actually non-trivial here, because even the OPT potentially could be working at different speeds at different servers. We don't know what it's doing. And if it is working at different speed, it becomes harder to lower bound what the cost is going to be. So we make a very simple enhancement to the system. So rather than For the OPT, rather than looking at a series system, we actually turn it into a parallel system where any job which comes in can be simultaneously processed at all the servers at the same time. See, the initial condition is that every job should go through all of these in series, one after the other. We're just making an enhancement that a single job can actually be processed at the same time by all the servers together. What that does is all the servers with the OPT now are going to work at the same speed, which is very helpful. And then you can write that the lower bound on an OPT cost to be the number of jobs in the system, which is N0 of T, plus K times the single speed which is being used by each of these K. So there should be K plus 2 here. So K plus 2 servers here. So this is what this lower bound would not be possible if you were to just look at the series system where even the OPT could actually execute jobs at different speed at different servers, which will be very difficult for what I just suggested in the with the drift of the potential function we constructed. So we're enhancing the OPT on one side and we are analyzing what our algorithm is doing and somehow able to compare that even the enhanced system for OPT is at most a constant away. So the upshot of all this is that the algorithm is running jobs serially, the OPT is running jobs parallelly, and still the difference is only a constant. So it's actually a stronger statement to make rather than just saying that for a series system, we have a constant competitive ratio. All right, so now we can go to a more complicated system where we don't have just a line network, but there is a series parallel network. So there are multiple branches of this, and in each branch there are K servers. So this is going incrementally in hardness of the network. So now what you can do is you can similarly define as before some algorithm. So because all these parallel paths are identical, the routing is going to be round robin, and the speed of the source is going to be some complicated function now of the total number of red nodes in the network. So red nodes in the network mean that they have at least one packet outstanding with them. That is what the red nodes in the network is. So using that, you can define that. The important thing is now the different nodes in the network are going to operate at different speeds. So speed of the source is going to be defined by this quantity, but speed of any internal server is going to be 1 by P of the speed of the source. So there are P parallel paths. So each of these series paths are going to work at 1 by P of the speed of the source server. And what you can show again is that the competitive ratio is a constant. For alpha equal to 2, we can show it to be 54. So it's large, but still a constant, and remains independent of the network, where network is defined by the number of paths and the number of servers in the system. So I had hopes of saying something more on this, but I think limited time, I'm going to skip few of the slides and go to the most challenging network with the worst case.
Is the problem easier if it was just a parallel network?
So what do you mean by just a parallel network?
Meaning no series queues. In series, there's only one queue, but all of them are in parallel.
So here we are saying anyway, it doesn't matter. So the answer we are going to give you is independent of the number of servers in that queue. So now let's look at the general network where there is a star. So it's not as general as you would like. So what we are going to assume is that between every source destination, it's still a series parallel network, but across different sources destinations, it can be whatever network it can be. So it's not as general as you would like. And here we have to define a quantity. So let's look at any node in the network and look at the number of paths which are crossing it. So remember, paths are well defined here because we're assuming that between every source and destination, it's just a series parallel network. So you look at the number of paths crossing a particular node and find the node which has maximum number of paths crossing it. So the algorithm is going to be as follows, that each source is going to use round robin over its parallel paths like before. All the so any internal node in the system here is going to process all these packets coming from distinct source destination pairs simultaneously. So now each source is going to process more than one job parallelly. But the speed of the job is going to be scaled down with respect to P inverse of this quantity 1 by D max to the power alpha minus a tau, which tau is a parameter we can choose. So D max is essentially, you can think of the maximum degree of any node here. And I'm scaling down the speed of every node with respect to a single series parallel network as P inverse of 1 by D to the power max to the power alpha. And where SV is the speed of a node you would choose if there was a single source destination pair. So what is happening is because of multiple source destination pairs in the network, we are actually decreasing the speed of the network by amount which is driven by the maximum degree of any node in the network wrapped with a function P inverse of that. And that is again required because otherwise there will be too much power consumption and you will get a competitive ratio, which is something like order D max to the power alpha, which is too large. So you need this compensation to get something non-trivial. And your parameter in hand, which is the tau. So the result we can give is as follows, that for power function of the kind P of S is equal to S power alpha, the competitive ratio scales as D max and not D to the power 2 or 3, which it could if it was a non-trivial result. Essentially extending the series parallel network would give you something like D max to the power alpha, but by decreasing the speed, doing few more things, one can actually bring it down to order D max. So essentially D max is the congestion in the network and the competitive ratio is scaling as the congestion of the network. But at least it becomes independent of alpha for reasonable values of alpha. All right, so let me now go to the stochastic case, skip this and go to the stochastic case.
Rahul, I have a few comments.
Right.
So I see that your routing algorithm is not adaptive. So it is not taking into account the number of jobs that it has on the paths. So
Yes.
we looked at this problem from throughput optimization in a general network without any assumption.
Mm-hmm.
And I don't know whether you are aware of it. It's called the universal max weight. And we showed that if you take into account the load on each path and you just compute the shortest path, you do routing according to the shortest path, but the shortest path is defined in terms of the number of jobs that you have on the path.
Right.
So it's a weighted graph.
Yeah.
Then you can prove guarantees again, not on this adversarial case, but on the throughput optimization case.
Right.
So yeah.
That's
so is there any possibility that I can use that kind of ideas to extend this problem to general networks without any assumption?
Yeah. So in the worst case, I don't know, but in the stochastic case, it will turn out you won't need it. So I'll just present that. So in the worst case, I don't know if I use that information. I do, but in stochastic case, you don't need to.
So in the worst case, it is still open, right? I mean, there is no. There is no result. Okay.
So for the moment, the guarantee we are given is still a function of the maximum degree of the node, and we don't have a matching lower bound.
Right, right. And do you think like this non-adaptive routing is optimal? I mean, not taking.
I would not conjecture anything.
Okay.
Things become extremely difficult in the worst case. So.
Okay. Okay. Thank you.
So now the stochastic case, things are slightly more interesting and structural. So let me do that now. So now instead of packets arriving, we are going to assume that each of the sources are going to get data arriving according to a Poisson process with rate lambda. And now what the speed of a server essentially means is the exponential. So if you remember MM1Q, where the arrivals are Poisson and each server is essentially, or each job has a IID service time defined as an exponential mu. Similarly, the speed here is going to essentially, you can think of it as bringing down the service time of a particular packet. So packets are not really distinguishable. Each packet has an IID amount of service to be done, and that is distributed according to a mu. We can fix that mu ahead of time. When the source is operating at speed s, it's just bringing that mu divided by s. So that is what it's doing. And again, we're going to use P of S as S power alpha. So earlier, the objective function we defined, it was for a set of packets, and that is why this integral was well defined. But now in the stochastic setting, the time is of infinite horizon. So I'm going to slightly change the objective function and take it as an average. So essentially what it's going to look like, it is the expected number of packets in the system at any time t plus the expected amount of power spent by all the nodes in the network. So that's the only change with respect to the arbitrary case or the worst case arrival case that happens to the objective function. And now again, what we want to find is the routing. So if lambda 3 is the total arrival rate coming into source S3, how it is going to get routed over all its different paths from S3 to D3. So that's one question. And once you've done that routing, it's not one after the other, it's actually interdependent. You look at a particular node V and look at all the flow which is going through. You have to choose a speed for each of these nodes depending on what flow is going through that process. So the decision variables are again routing and the speed choice. So we're going to directly lower bound the cost of OPT, which is also going to give us the algorithm. So think of for a particular path from S3 to its destination, the amount of flow is lambda 3 comma p. And for some other source, it is some feasible flow, which is lambda 1 comma p. Look at any particular node in the network and count all the flow, which is, so we're just fixing one particular feasible flow for all sources in the network. And look at a particular node and count how much flow is going through that particular node B. So this is the total flow which is going through node B. This is just a feasible flow. We don't know what is optimal or not. So now what we're going to say is that for any feasible flow, you can bound the cost of energy this node V is going to pay. So cost of V, just in terms of power, is going to be the expected amount of speed at which it's going to work. So S of V is the speed at which V is going to work. And you take the expectation with power function V. So this is the total power or expected power you're going to spend for that particular feasible flow on node V. Now, Jensen's will give you the fact, because P is convex, that this is at least P of expected value of S of V. And now for stability, that given that the total flow through the network is lambda V, the average speed at which you're going to work is at least should be lambda V. So that just gives you that the energy cost paid by a node V has to be at least P of expected value of lambda V.
So Rahul, I missed this. Are you allowing for dynamic scheduling of power rate depending on the
whatever? This is just an expected answer.
So, but in your algorithm, will you allow for?
So algorithm won't need. Yeah, algorithm won't need it. This is just a lower bound.
This is just a lower bound, of course. Yeah.
So lower bound is just counting the total amount of power a node V has to spend for any feasible flow.
Okay.
So for any feasible flow, you count the total amount of traffic going through node V. The total amount of energy you have to spend is at least P of the expected value of lambda. And for P of S is equal to S power alpha, we just look at this program now. So this is nothing but counting this particular lower bound across all nodes in the network. Just count this thing and try to minimize this with respect to all possible feasible flows. So what we did was we fixed a feasible flow. We looked at what's the least power a node has to consume. And now we are trying to find the optimal flow given that this is the power you have to spend. So the internal rectangle is nothing but for each node V, how much power you have to spend. The alpha comes in because the power function is P of S is equal to S power alpha. And you're minimizing with respect to all the feasible flows in the network. So it's conceptually, it's a very simple lower bound. With isolating a particular node, looking at all the traffic going through that, look at what's the least power you have to pay to service that, and then just try to minimize overall possible feasible flows. So that's just a lower bound. It's doubly useful in the sense that what we are going to do is we're going to look at the optimal answer this is going to give you for routing and decide that in defining an algorithm. So we're going to make it dual purpose optimization problem. On one side, it gives you a lower bound on the optimal cost, and the optimal solution of this with respect to lambda IP is also going to be used to define the algorithm. So the algorithm is going to be following. So solve this problem, which is always possible to solve. It's a convex problem. So whatever
any structural insights that you get from solving this problem,
we'll come to that in the competitive ratio. We'll get it very easily.
Okay.
Right. So suppose you can solve this problem, which is a convex problem. The algorithm is going to be defined with respect to the optimal answer that convex optimization gives you. So for a path P on the ith source destination pair, let this problem tell you that to route lambda star of IP amount of traffic. So that's what the algorithm is also going to do. The algorithm doesn't tell you what speed to use. So speed choices are under our control. So what we are going to make is for each node V, look at all the traffic that is passing through it under this optimal solution. So that is lambda star of V. We're going to add a fudge factor just to make sure that everything works through. So that is a factor defined with respect to alpha. So alpha is the exponent of the power function. So this is essentially, you can think of, you need slightly more anyway for stability. We are making sure it's sufficiently more for our analysis to go through. So the competitive ratio ends up being for this algorithm has two parts. One is a part which only depends on alpha. So theta alpha is just some function of alpha. You can compute it for any alpha you want. The theta network depends on the network. And what that tells you, this is where all the structural insight is sitting inside. That for the ith SD pair, let L of P be the hop length of the path P. So there are lots of paths from source to destination. L of P is just the length of a particular path. Look at the minimum across all paths in the network for that particular source destination pair. And this is the ratio of those two quantities. For a particular path, that's the hop length. And the denominator is, among all such paths, look at the minimum possible length path. So shortest path. Multiply that with the optimal answer you got from your convex program. Sum it across all possible paths and divide it by 1 by lambda. Remember, summation of lambda I star IP is nothing but lambda I itself. So just this summation is exactly equal to lambda I because of the feasibility constraint, that the total amount of traffic carried at least has to be as much as the total amount of traffic incoming into the system. So the only weights we are associating is the ratio for a particular path, which is length of the path divided by the shortest path available in the network. And the theta network, the eventual guarantee is in terms of max of all possible source destination pairs. So now let's look at if we can interpret this. So it's actually a very nice interpretation. So suppose for the ith source destination pair, the maximum length of any path and the minimum length of any path is bounded by a constant. That we take a network, we isolate a particular source destination pair, and among all possible paths, you look at the length of the maximum length path and the minimum length path. If that is a constant, this theta of I solves out. So as I said, the summation of lambda star IP is nothing but lambda I itself. And if this quantity is upper bounded by C for all paths, what you end up getting is that theta I itself is a constant. So if a network is well behaved in the sense that the length of the maximum path and the minimum path is not too different in terms of their multiplicative ratios, you're going to get a constant competitive ratio. Alternatively, what could happen is that the length of a particular path is very large compared to the minimum or the shortest length path. And let's call it some function G, and mod V is the number of nodes in the network. So suppose that happens. In that case, what is going to happen is that the lambda star IP, the amount of traffic routed through this long path, is commensurately going to be smaller because you have a shorter length path and you're unnecessarily also looking at very long paths. When I say G, it's essentially scaling as something in terms of N as the number of nodes in the network. So automatically the weighting fraction here, which is lambda star of IP, is going to be small for paths which are very long. So even in the case where there is huge difference between the length of the paths for a particular source destination pair, the optimization problem automatically is going to control the amount of traffic routed through long paths compared to the short paths. And we're again going to get something which is theta I small. So if it's a well-behaved network, you get a constant anyway. Even if it's a very heterogeneous network in terms of length of the paths, the optimization problem is going to make sure that the competitive ratio remains small. One can't give a simple answer on upper bound, but because this optimization problem is readily solvable, you can always evaluate. So suppose you're given a particular network, you can always evaluate what the competitive ratio is going to look like. So that's the good part about it. It's not a cumbersome exercise to compute the competitive ratio.
So Rahul, you're assuming that you know the arrival rates, right?
Yes.
What if I don't know the arrival rates? So the general optimization setting.
So this is the main difference between the typical throughput optimal literature and our work. So here one has to possibly implement another learning module to learn the arrival rates. But for the moment, you're assuming all the arrival rates are known to us. Yeah, that's a good question. So for many algorithms, one doesn't need to know what these lambdas are, but for us, we need to explicitly know what these lambdas are. So let me wrap it up. So essentially the upshot of all this is that speed scaling in networks is a complicated exercise. We have only started to look at it carefully now, and in no ways it is complete. Even for the smallest line network, we don't know converse in the sense that we don't know the guarantee we are getting is actually tight or not. We believe it is not too far away from being tight, but we have no proof for that. In the most general network, the guarantee is in terms of the maximum degree of the network, which is bad. The conjecture is that it may not be linear in Dmax, but at least it's some power like 1 by alpha or 1 by 2 alpha power of Dmax. the proof eludes us for the moment, but there is hope. At least one can show that it can't be independent of Dmax. It may not be linear in Dmax, where Dmax is the maximum degree of the node in the network. For the stochastic inputs, I think one gets much nicer answers. There are structural results one can get, and on the same time, for most networks, you can consider the competitive ratio is going to be a constant. We don't expect one to construct a network where constant competitive ratio will start scaling with the nodes in the network. And with that, I'll stop.
Thanks, Rahul. Questions?
So I have a right.
Go on.
I think somebody else is speaking.
Go on, please.
So I have a comment. So regarding your the stochastic analysis, I mean, the first part that I would like to do is to replace the assumption that I don't know the arrival rates.
Yes.
And what I think is that, I mean, if you just take inspiration from the throughput optimization literature, then you just replace these arrival rates by some sort of the queue length or the number of jobs that you have on the servers.
Correct.
Right.
The only problem is that because you want both lower and upper bounds, the lower bound is inherently dependent on that.
Yes, absolutely. It depends on that. But I don't think, I mean, do you think that you need to know the value of the actual lower bound of the optimization optimal algorithm for running an online algorithm? So do you really need to evaluate what is the lower bound for the algorithm?
What you're asking is a more interesting question. For the moment, because we want an explicit control over the competitive ratio, we went through this particular exercise. But by no means, this is the only way to do it.
Right. Okay. Yeah. Okay. Good.
Or can you just go back to the slide where you showed the ratio for the stochastic case?
Yes.
Sum over IP.
This one?
Sure, this one is fine. Yeah. I mean, in a sense that, like, is it clear that your worst case actually has multiple source destination pairs? I mean,
we don't need to know that, right?
The worst case just.
So yeah, I don't know what worst case is going to look like. I'm just giving a guarantee which is.
No, I know, but I'm saying that we somehow. Sorry, I think my voice was breaking.
I completely missed what you said. So the network was bad. Can you say it again?
Sorry, I was just saying that if you could show that the single source session case is the worst case, if you could just focus your analysis over there, and that might be easier to analyze. That's all.
Could be. Yeah. But eventually, see what it's doing is essentially it's separating out the sources anyway. So if you look at this theta network, it's a max over all possible sources. Only thing the coupling is happening is via this lambda star of IP. So if there are more sources in the network, the lambda star is going to be larger. So what you're suggesting may not actually work. Is this clear why lambda star IP couples all these sources?
Yeah, no, I can see that.
So that is where, so if you take a single source, you may be able to show something, but that may not be the worst. See, all we are saying is that in
That's
this,
not that straightforward, I agree.
yeah, what theta of I is capturing is that the ratio of the longest path versus the shortest path. It's immaterial what lambda star is. That is what is very interesting. That summation of lambda star IP is always equal to lambda I. So as long as you can bound the maximum versus the minimum length of paths for any particular source destination pairs, you're okay. And if it's not bounded, then lambda star IP is anyway very small. So it's either way, you're going to be safe.
Yeah, no, you're right. I see that. Okay.
So we can't give a universal answer for any network, but the interesting part is that you solve this convex program and you get an answer for yourself. So that's the good part about this competitive ratio. A general or a more interesting answer would be an independent of the network, but that is for the moment not available.
Okay.
I had a question. So for the case when alpha is equal to 2,
Yes.
I mean, is anything to be gained by viewing this as some network of resistances where the power is like, I squared R?
So yeah, I know people have done this in network theory, but at least for speed scaling, we don't know if that helps. Thinking of this as resistances. So it's a good point, but neither in the past work nor in our work we have looked at it that way.
Okay.
Okay. Other questions? All right. Doesn't seem to be. Okay, so we thank Rahul again. Thank you, Rahul.
Thank you.
And
Organizing.
it's a pleasure.
Yeah, thank you for organizing
And,
the Friday.
yeah, it's a pleasure. Yeah. Okay, so let's end the meeting then.
All right.